Hello. All right. So the next section is 5.2, and again, it's not going to line up exactly with the page numbers in your workbook. Sorry about that, but it is the same idea and same information. So this time we're going to talk about something called inverse functions. Now, intuitively, you guys know what inverse. You're already doing it a lot. We just haven't given it that name. So inverse operations is the stuff we do to go backwards and get us back to where we started. So, for example, if we're starting with x and if we subtract 3 to go backwards, we're then gonna, see, after we subtract 3, we're gonna add 3, right? If we start with x and we subtract 3, and suddenly we add 3, what do we get back? X minus 3 plus 3, we just have x, right? So addition and subtraction are examples of what they call inverse operations. What's the inverse operation of multiplication then? What's the opposite of multiplying? Well, the opposite of multiplying is division, right? And what would be the opposite of a square root? Squaring. So what's the opposite of a cube? Cubing something, or specifically, raising it to the third power. So what's the opposite of raising to the fifth power? Well, taking the fifth root. And just so we're speaking the same language here, if the opposite of multiplying is dividing, right? The opposite of a cube root is cubing something. The opposite of taking something to the fifth power is the fifth root of something, right? If I stick x in there just to have something in there, okay? But not every operation has an inverse. And if we use -3 as an example, and we try the operation of squaring it. Okay, well, -3 squared is 9. So if we wanted to go backwards to get back to -3, the opposite of squared is square root. But we take the square root of 9, we get +3. That's not exactly what we started with, right? So that's not back to our original number when we only took one of the square roots. It didn't work for us. So we have to be careful because not every operation has an inverse, right? Or doesn't have a simple inverse. We'll put it that way. You have been using inverse operations for years. Every time you're doing algebra, whether it was in your head or on the paper. Like if I told you to solve 5x plus 3, well, you're like, well, the first thing I do is subtract 3. Why? Because it's the inverse operation of adding 3, right? So I don't like the way it's written on here. I'm going to do this off to the side. Hopefully it looks better in your workbook. We subtract 3 from both sides because that is the additive inverse of adding 3. And then we get down to here and we're like, oh, well, what's the opposite of multiplying by 5? Well, we'll divide by 5, right? You guys have been doing this for years and you're really good at it. It's just now it has a name, right? We did the inverse operation here. The inverse of multiplying was dividing. The inverse operation here, the inverse of adding was subtracting. Now, when it comes to inverse functions, now I want you to notice inverse operations versus inverse functions, okay? So an inverse function, and a function has an inverse if the domain, if the domain of f for all x in the domain of f and for all x in the domain of g, that if we stick f into g and we do the opposite order, we stick g into f, if when we do that, we get x, exactly x, not 2x, not x squared, not x cubed, but exactly x every time, if we get back to x, then it's an inverse. Then those two functions are inverse functions of each other. Like multiplication and division are inverse operations. F and G would be inverse functions if You plug one into the other and you get x, and then you go backwards. You plug the other into the first and you still get x, and they're inverses. So, and then this is the notation. This is how you write it with that little exponent of -1. That's the inverse of f of x. So when they ask this example here, are f of x and g of x inverses of each other? Okay, well, the way we figured out is we take one and we plug it into the other one and see if we get x. Then we do it in the other order and see if we still get x. So my outside function, I'm going to plug in 1/3 x minus 2 everywhere I see an x. So that outside function says 3 of x, except I'm not plugging x, plus 6. And I'm going to plug in, instead of just x, I'm going to plug in all of g. So 1/3 x minus 2. Distribute it and clean it up. 3 times a third, 3 times -2. Ooh, we did get x. So far, so good. Now we have to go backwards and see if it's still true. And I want to do this on the same page. On the way mine's printed, it shows at the top of the next page. I don't know what it looks like for you. But now I'm going to pop it on here because I want to go backwards. Find g of f of x. So my outside function is g. My inside function this time is 3x plus 6. It's f. So my outside function this time says, okay, 1/3 of whatever x is minus 2. All right, let's try it. 3x plus 6 is what goes in there. So distribute. 1/3 times 3x is x. 1/3 times 6 is 2 minus 2. Yes. Both g of f and f of g equal x. So yes, they are inverses. That means one way I could write that is I could say that f inverse of x is the same as g of x. The inverse of x equals g of x. And I could write it the other way too. I could say the inverse of g equals f. So that was on previous page right here. That was terrible handwriting. Therefore, f and g are inverses. Now, that was symbolically. Now let's talk about, okay, if we look at a graph, just like we talked symbolically with whether something is a function, but then we can also talk about a graph like the vertical line test. We can talk about inverse functions symbolically or in a graph. Okay, so let's look at the point here, 0, -2. Notice -2, 0. Well, those are inverses of each other. Let's look at another point, 6, 0, and 0, 6. Those are inverses of each other. If you just switch the order, if you switch all the x's and y's, you get the inverse. Now you notice though, what is it? It looks like it's almost symmetrical, right? It's almost a mirror image reflection over something. Remember, if we do one, we plug one in the other one and we switch it, what are we going to get every time? We're going to get x. So the line that these graphs of inverses, if they're inverses, the line that they will be symmetric about is actually the line called y equals x. Ka-ching, right? Okay, now again, we've talked about that not every operation has an inverse, not every function has an inverse. So if it's an inverse, if it has an inverse, two things has to be true. First of all, it has to be a function, right? So vertical line test tells us that it is a function. if we're looking at the graph. To be a one-to-one function, it has to pass vertical and horizontal line tests if we're looking at the graph. Okay. And the way that this talks about that is it says, to be a function, each input, each x, has to have only one output or y. To be one to one, each output is also getting only one y. So the x's and y's don't repeat if you got a list of them. So if we look at this real quick, um, example, this function is one to one. Each input goes exactly to one output, right? We're saying that it passes the vertical line test, although my vertical lines are terrible. Okay, so that's a vertical line test, right? But each output also goes to exactly only one input. So each y value only gets one x value. Each y value only gets one x value, right? So you can think of that as horizontal line test. Okay, so this function is not one-to-one. Why? It passes the vertical line test. So it is a function. It is a function, but why is it not one-to-one? Let me see. If we draw a line almost anywhere on this graph, a horizontal line, it's going to have that y value. Let me do better. Let's do y equals -3. More obvious. That y value at y equals -3 has two x's going into it. So it does not pass the horizontal line test. So it's not one-to-one. It has to pass both of those for it to be one-to-one. Okay. So that's when we're talking about the horizontal line test. Okay, so you can draw all these horizontal lines and it's fine. Draw a horizontal line almost anywhere on here and it's not fine. That's much prettier than the craziness I just drew. Now, if we're given a function, how do we find the inverse if we know it has one? Okay, first we have to check to make sure it's one-to-one. And if it is one-to-one, then we start by we take out the function notation name and we put in just y. Okay. Then we're going to switch the x and y and solve for y. Okay. So we'll talk some more about that here in a second. Here's an example graph f of x and f inverse on the same graph. So if you didn't have that other graph on here, this is the point 0, -3. So suddenly the new graph, the inverse has a point -3, 0 on there. Okay. We have another point 2, -1 on f. Then we're going to look for -1, 2 on f inverse. Okay. All right. Find the inverse if it exists. All right. Well, let's try it. First, we're going to switch this. We're going to rewrite it as y equals. Then we switch-a-rooney the x and y. Switch-a-rooney. Switch-a-rooney. Switch the x and y, and then solve for y. So let's see. We want to get y by itself. We're going to subtract 6. So we have x minus 6 equals 3y. And then divide by 3. Divide by 3. So x minus 6 over 3 equals y. Now, this new y, we're going to rename it f inverse. Whatever the name was originally up here, we stick that inverse on it. And that's what we're naming this guy. New name for the new version. Okay? All right, let's try it again. So y equals cube root of x minus 3. All right, switch the x and y. and solve. So the opposite of cube root, cube everything. Now that works. We can do that because um, if I plug in a negative number, I'm going to get a negative cube when I take the cube root. Whatever I plug in, I get out. So if I plug in a positive into a cube root, I get out a positive when I cube it, and vice versa. Negative and negative, it's all cube. It's all okay because it's an odd exponent and an odd root. So we can totally do this legally with no problems. So x cubed equals y minus 3. Opposite of minus 3 is add 3. So x cubed plus 3 equals y. Rename it because this is the inverse. We did it. F inverse is x cubed plus 3. Good job. Okay, now let's think through real quick, make sure we're good to go. If this is a line, are lines 1 to 1? Yes. So it does have an inverse, so then we can find it. This is a cubic function, right? So something like this. And yes, that is 1 to 1. It passes a horizontal and vertical. So yes, we can find the inverse. This guy, oh, Miss Flannery, started getting all excited and started switching X's and Y's. But what happened here? This is a quadratic of some sort. I actually didn't graph it in the right spot, but it's a quadratic. Do quadratics, are they 1 to 1? No. Does not have an inverse. They are not 1 to 1. So no, F inverse here does not exist because quadratics are not 1 to 1. Not 1 to 1 functions. 1x for every y and 1y for every x. So we don't do that one.